All right, the next presentation is going to be RelocNet, Continuous Metric Learning Relocalization using Neural Networks. And the presenter is going to be Vassileios Balntas.
Okay. Hello, hi. I'm Vassileios, and I will present our work. It's called RelocNet, Continuous Metric Learning Localization using neural nets. And this is work that we did with Shuda and Victor Prisacariu in the Active Vision Lab in University of Oxford. So first of all, I will describe what the problem is. So imagine there's a scene, and then we have some person with a phone walking around, and this leads to the green trajectory you see there, the path. And using some method, for example, structure for motion, we get some ground truth poses for this trajectory. So for each RGB frame from the camera that the person uses, we have an associated pose with it. And then we have another person walking around, which leads to the red trajectory. And our goal is to use the frames from the first trajectory with their poses to find the poses of the new red path. So this approach has been tackled with traditional geometry methods or depth, but we will focus more on RGB-only methods and CNNs. So the first solution, generic solution to this problem using CNNs is to just directly regress the 6D pose of the camera. So we have a network that uses the training frames that have ground truth poses to regress each individual frame, and then we test it on unseen images, and then we hope that it regresses correctly the 6D camera pose. As you can see the equation there, there's the loss is based on translational and orientational component. This introduces a few problems, such as the scaling parameter between translation and rotation. But also the most important problem is that it has to be retrained for each new scene, because the origin of the world is related to the individual scene. Another way to solve this problem would be to use more large-scale retrieval methods. So these are transferable, so they can be applied to new scenes. They work so for example, one example of such methods is to use triplet networks to learn descriptors, global frame descriptors, such that the distance between the anchor that you see there and the positive, which represent the same place, is smaller than the distance between the anchor and the negative. The limitation of this approach, however, is that because they're only trained to be place invariant, they don't know anything about the camera poses. So our motivation was to use both methods, let's say, get the best of both worlds, and learn global frame descriptors that are transferable to new scenes, and they're suitable specifically for camera pose retrieval. And also to combine this retrieval with some extra relative pose estimation to get even better poses as a result. So the overview of the method can be seen in this slide. So we see on the left that we have some training images that are stored in the dataset, and we know the poses for these images. And then we have a new unseen query, which is the one with the green outline, and we use our trained descriptors to find the nearest neighbor, which is in this case the red one. Then we apply our relative pose network to further improve the estimation. First, we transfer the pose of the nearest neighbor, and then we apply the relative pose estimation to further improve the final estimation. And you see the cameras on the right. The red camera is the camera position of the nearest neighbor. The white is the ground truth, and the green one is our estimation after the network is run. To do this, first of all, we have seen empirically that the classical relocalizers, for example, feature-based methods, they work very well when the overlap is maximized between the query and the retrieval. So to learn this, we propose to use a continuous metric learning approach that tries to maximize the overlap, the covisibility of the scene between the two scenes, so that the classical methods can work even better, let's say. And to do this, we simply introduce the frustum overlap between a pair of poses and their images, and which is simply the amount that they overlap, which is, if you see here, the yellow part of the images. And because we normalize this by the union of the volumes, this is a number between 0 and 1, where 1 means that it's exactly the same camera position, and 0 means that the two scenes are not related at all, that the cameras look at completely different directions. And the way to learn this is simply by using a Siamese model, where we give as inputs the two images, and we also compute the frustum overlap, which is again denoted by the yellow area there. And we try to learn our embeddings from the feature network to be the distance between the two embeddings to be exactly the same as the camera overlap. In addition, because as we said before, we want to also improve the final estimation, we also add a pose layer in the end that tries to regress the relative pose between the two cameras. So in the inference phase, we can just use this and the pose of the nearest neighbor to update our prediction about the unknown query pose. Some implementation details is, of course, that we need the camera intrinsics to compute the frustum. We also need to set maximum clipping depth so that we can control the size of the frustum, which is something related to the scale of the scene we're looking at. And for training, we use the ScanNet dataset from DAI and the others. And for testing, we use the 7 scenes dataset from Blocker and others. So for some retrieval results, here we plot, here we saw the percentage of the nearest neighbor that was correctly retrieved above a specific threshold, which in this case is 60%. So that means that we retrieve the nearest neighbor and then we check how many times it was actually had a high overlap with the ground truth. And we see that our method is able to significantly increase the retrieval performance compared to other methods, and in some cases even 30% more in terms of success rate of high accuracy nearest neighbors. Some more training details is in this experiment we used, as we said, the ScanNet dataset to train, which has lots of sequences. So what we did is we kept a small part, different sets of the training sequences to see the effect of the training size in our descriptors. And we clearly see that when we're only using 10 sequences, then the whole method easily overfits. But when we add more sequences, then everything's okay. So this is important because, as we said before, most works in this area, they test with the 7 scenes dataset, which only contains 7 scenes. So this shows that we need more scenes to do accurate training for such large-scale methods. Also, we can see that if we plot the success rate in terms of the overlap threshold, so that means that the more right we go in the x-axis, the more strict we are about what we consider successful relocalization. We see that our method is able to deal with it across all possible overlaps, so for high accuracy and for low accuracy cases. Here we also saw some pose regression results, which comes from using the full network to both do the retrieval and to regress the final scene. And for the column next to the last, we saw the results when we train our method in ScanNet. And for the last column, we saw the results when we train and test on 7 scenes on the train and the test scene of each individual scene. So we see that our differential pose regression works very well in terms of comparing with previous works, and in most of the cases either is similar or outperforms the results. And it's also important to see that even when we train on another dataset and we use the network to test on 7 scenes, so there's no overlap between the training and the test scenes, it still gives somewhat reasonable results, and even can be used for, it's comparable with some other cases. So that shows the power of the retrieval process of our whole system, which is transferable to new scenes. So for some qualitative results, you can see here we have plotted the blue frustum, which is the ground truth. The red frustums come from the nearest neighbors, and then the cyan ones are the ones we predict after we apply our network. We can see that in the first 2 cases it works reasonably well, and it brings the prediction closer to the ground truth. And it's also interesting to see the third case, where we see that the blue, the ground truth, is very far away. So the retrieved neighbors were very far away from the scene, so they were not good quality networks. So in that case, our network wasn't able to do much because the neighbors were very far away. Also, because as we said before, currently 7 scenes is the thing that most people use in this area. So we wanted a more large-scale dataset that is able to assist in experiments in terms of relocalization. So we introduced the RelocDB dataset, which has 500 sequences with their camera poses. And the important thing is that we do 2 loops over the same scene, so that makes it suitable for relocalization experiments. And then you can see some examples of the sequences that are in the images below. So, yeah, to summarize, first thing to take home is that learning something with geometrically meaningful losses, it leads, of course, to a more geometrically meaningful descriptor in the end. And the second thing to take home is that our RelocDB will be available soon. And if you want, you can sign up to be notified on release, which should be really soon. We're just trying to do the final things before we release it. And yeah, if you want to discuss more, we'll have more experiments in the poster. Hope to see you there. Okay. Thanks.
If there are any questions, please come to the microphone.
Hi, thank you very much. Very nice talk. Do you have an idea of how your retrieval part compares against NetVLAD or any of the other trained retrieval parts?
Yeah, we have this experiment on the poster, so you can see later. But yeah, it's better, and it's also especially better when we only have a few. So we did this experiment that we only keep a very small part of the training set. So instead of using, let's say, if we have 1,000 images with their poses as a training set, we said, okay, if we drop 900 of them and we just keep 100, then we see that it improves much, much better than NetVLAD. So in terms of accurate pose retrieval, it seems that it's significantly better. We can discuss the results later. I have them on the poster.
We have time for more questions. All right, maybe in the meantime, I'll ask one. So for your pose estimation, you feed the output of the network through 2 layers to transform it into a rotation matrix. Have you tried direct regression, and do you have some intuition on why this might work better or worse?
I've tried the quaternion-based, so similar to Posenet, and it seems that the results by regressing the matrix are slightly better, and it might be because we're regressing in the end valid rotational matrices, but in the quaternions you need to normalize them in the end in order to make them valid rotation representations. But in our case, because we use the layers, the specialized layers, in the end they always output a valid rotation matrix. So it seems that it's slightly better.
Okay. If there's no more questions, let's thank the speaker again.